Assalamu alaikum. My name is Ahmed Merzoug, and I have just defended my PhD at the University of Texas at Austin. And this is going to be a recording of the PhD defense presentation. So feel free to watch it and ask question in comment if you have any questions. I would be happy to answer those. So this work have been done under the supervision of Dr. Michael Perch at the University of Texas at Austin. My committee member were Dr. Daigle, Dr. Zoya, Dr. Masha, and Dr. Hongon. So the presentation of today is going to be about generative artificial intelligence for subsurface modeling, history matching, and uncertainty quantification. The aim of this research is to develop workflows and tools that can allow the adoption of generative artificial intelligence for this practical application and the extension of some application that exists in the literature. So let's get started. So the agenda for today, we're going to start with an introduction, the research objective, model checking and comparison, generative AI for history matching, generative AI for uncertainty quantification, and then we're going to conclude. So let's start with the introduction and what are the research objective. So this dissertation tried to tackle three main objectives, or three main challenges that are in the subsurface. So the first challenge is going to be subsurface modeling. And for subsurface modeling, what we are looking to build tools that are very fast in generating model and allow us to constrain to both our geological understanding and for data conditioning. And by data conditioning, we mean the measurement at the level of the well location. So if we look into the current traditional approaches of geostatistical approaches that exist in the literature, we see that there is a trade-off. You can either go very high on reservoir heterogeneity or very high on the level of data conditioning or the number of data that you're trying to condition. So the problem is that none of these workflows allow you to have both of high reservoir heterogeneity and high data conditioning. And here where generative AI can allow us to navigate through all of this square where you can have different level of data conditioning and different levels of reservoir heterogeneity. Regarding history matching, if we look into some of the practices of history matching, we will see that a lot of people use multipliers. And the use of multipliers is like creating a local zone where you enforce that your data is matching the performance of the well. This breaks the geological understanding of the system and turns the problem from solving a physics problem into a mathematical problem where you are just trying to match curves. Another challenge is that every time we change the seed number when we build subsurface models, we're going to end up with a slightly different realization. A good example is here. We do have four realizations. All of these realizations honor the well logs and the measurement at the level of the well location, but each have a different continuity and a different distribution of channels. So which one should we use in order to do history matching approach? The other challenge is that if we use automated history matching algorithms, the size of these realizations is in the order of hundred thousands to millions to billions of cells. So how can we optimize this high-dimensional problem? So generative AI is here as a solution to reduce the dimensionality of this problem and allow us to use optimization algorithms. This is an example of history matching that is performed in this study. The third objective is uncertainty quantification. And when we talk about uncertainty, we are here specifically talking about scenario-based uncertainty. The issue with quantifying this type of uncertainty is that there is a lot of iterative process that goes into building these subsurface models. And this iterative process is the result of making assumptions. And if you change this assumption, you need to redo all the work. So let's take an example here. Let's assume that this is our reservoir, and then two geologists. One of them is going to tell us that the problem could be solved using sequential Gaussian simulation, and another one is going to say no, it should be used object-based modeling. Making this assumption of which approach to use basically neglect the other uncertainty that exists within the other model, which could also be plausible. Then every model of these have different parameters to use. For example, it could be a range and like variogram properties like the range, the azimuth, and even those have uncertainty in them. If you assume you know them, you also neglect other uncertainties. Here, an example for object-based modeling could be the number of channels, could be the width of the channels, which are still uncertain parameters. So all of this we call it scenario-based uncertainty. And then there is another type of uncertainty, and it is related to the nature of the algorithms that are used in traditional geostatistics. And this is called geostatistical uncertainty. This uncertainty comes from the fact that most of these models are stochastic. So they follow a random path. And every time you change the seed number, the random path changes. So for every time you run a generation of realization, you're going to have a slightly different realization. And this is uncertainty in the approach that we are using. So what we are trying to propose here is a way to circumvent the assumption of parameters that are here, let's say for example here, and allow us to include all of this uncertainty into our workflow without the need to do an iterative process and go forth and back. So the solution to most of these problems that we are trying to propose here is what we call, or what's called generative AI. So what is generative AI? Generative AI is a deep learning model that tries to approximate data. So the generative AI model doesn't have input and output, but the generative AI model is trying to mimic the data that you have and trying to build a model that can generate data similar to the data that you have. Think of ChatGPT, for example, as a text emulator. So ChatGPT is a transformer-based deep learning model that try to mimic the generation of text. There are other models, for example, that try to mimic the generation of sound, other models that try to mimic the generation of images. And what we are trying to do in this study is to build models that mimic the generation of the subsurface models. So when you deal with generative AI, if you have seen previously, or you have done, or you have worked previously with, for example, ChatGPT, you will see that you're going to send a prompt, and then that prompt is going to go to the generative AI model, and then the generative AI model is going to give you an answer or a text, depending on the model that you're trying to use. Something that you do not usually see is this latent vector. And the latent vector is a Gaussian noise that goes into the generative AI model and ensure variability. So when you send the prompt, for example, if you send the same prompt multiple times, you're going to end up with slightly different answers, even though all the answers point in the same direction or the same answer. This Gaussian latent vector, think about it as a different seed number, is going to create that variability, and every time you send the same prompt, you're going to get a slightly different answer. The application of generative AI for building subsurface models is not new. There are several research in the literature that shows the adoption and the application of these approaches. For example, we have some work from our group at the University of Texas at Austin on 3D lobe depositional environment. There is other work on 3D fluvial deposition environment from Stanford. There is some work on CT scan, and this was the pioneer work of the adoption of generative AI for the subsurface from Imperial College of London. And there is also other work on 2D fluvial deposition environment, also from our group. So let's look into what is this latent vector and try to understand how does it work. So this is an example where we have generated 3 different images using the same prompt. So we took this prompt, generate an image of UT Bivu in a graduation ceremony 2025, and we send it to Gemini Banana model. We send it 3 times at 3 different prompts, and as you see, we see slightly different images, but they all point to the same direction, where a Bivu is in a graduation ceremony. The reason why there is slight difference is because of the latent vector. Every time we send a prompt, a different randomly selected latent vector is going to get inputted into the model. Something I would like to highlight is that as you use these commercial models, you're not going to have much control over this latent vector. But as we build our model, we can have control over that model and control how much variability we have or the directionality of the solution. Now, let's look into the research objectives of our study. First, if we look into the literature, we notice that most of the people rely on visual inspection in order to investigate the quality of their realizations. So what they do is that they look into the realization, and for example, here they see discontinuity, or here they see an isolated object, and they say, no, the model should not perform like this, and we refuse this model, and they retrain the model. There are other checks where people have been using limited quantitative checks in order to check their realizations, but these are mainly scattered, and everyone is going to have a different check for their realizations. What we are trying to do here is that we are trying to propose a standardized workflow that allows us to check generative AI models and see if we can trust them in order to be adopted in our modeling or our decision making. And the reasoning behind this is that these models are used to drive millions or billions of dollars investment. So we cannot really trust on subjective judgment or limited quantitative checks. We need uh, a standardized workflow that allows us to check how good of a models do we have. This problem had been partially solved by previous student Lei Liu, where she investigated the categorical data the generative AI used for building categorical subsurface model. And by categorical, I mean different facies. What we try to do in this research is to develop standardized workflow for continuous variables where that determine how much pore space or how much permeability do we have, for example. The second challenge that we are trying to solve here is the selection. If we look into the literature, we see that most of the researchers are going to be claiming that their model is better than all other models. But the problem is because of the absence of the standardized workflow of checking subsurface models, we see that there is conflicting results within the literature. Some researchers claiming that some models are better than the others, and others claiming that those models are better than the first ones. So what we are going to do here is that we're going to use the standardized workflows that we have developed in the first chapter and use it to compare the different models to see which models should we use and which model perform better for which task that we rely in geostatistics or in subsurface modeling. Next, looking into the history matching literature, we compare the history matching literature with the subsurface modeling literature. We do see that the generative AI practitioners that focus on subsurface modeling focus mainly on training their generative AI models on unconditioned realization. And this gives them flexibility and reusability of the model in order to condition to new measurement at the level of the well location. However, if we look into the history matching practitioner, we see that they train their generative AI model on preconditioned subsurface models, where the training subsurface models are already conditioned to measurement at the level of the well location. This limits the reusability of the model and the flexibility of the model, and it limits the reusability of the model, but it allows better conditioning for the dynamic response. And this is what the history matching practitioners care most about. So what we are trying to do here is to propose an approach that closes the gap between subsurface modeling and history matching and allow building practical and generalized approaches for history matching that is independent of the well location and the measurement at the level of the well location. After that, we look into the uncertainty quantification, and for the uncertainty quantification, we see that there is very limited application of the uncertainty quantification for building subsurface models. Mainly the application that we see is from Stanford, Song et al. 2021. And the challenge with this approach is that they try to modify the cost function. And the problem with the generative AI models is that they are unstable in their training. So if you add another hyperparameters for the cost function, it's going to make the training more unstable and more and prone to collapse the training, which is gonna need retraining several times until you come up with the hyperparameters that learn the practical that learn how to include the uncertainty quantification in the model parameter. So we see that the model approach are complicated, and what we're trying to do is that we're trying to introduce a simplified approach that allow us to include the uncertainty quantification in building subsurface models using generative AI, but this model need to be robust and does not cause more issues with the training instabilities. So let's look into the chapter 1 and 2, where we develop model checking and comparison of the generative AI models. So there are two challenges here. The first one is that the application of generative AI for subsurface modeling rely on visual inspection, and that there are several GenAI models, and there is no clear selection process in order to say which model should we use for which task. So the solution is that we propose minimum acceptance criteria protocol for checking subsurface models, and then we take that protocol that we have developed and we use it to compare the different generative AI models. So the workflow as follows. We develop checks, and then we generate training model using sequential Gaussian simulation. We train the generative AI, and then we generate realizations. We apply checks on those realizations, and then we compare the models that we have. So in this research, we developed 10 checks, and I'm going to go into each one of those in details and show the importance of each of the models. In the first part, we use as our training images sequential Gaussian simulation. And the reason why we use sequential Gaussian simulation is because we can have control over the spatial continuity of the system. So for example, we can have different variogram ranges and that control the spatial continuity. And with this, we can see if the spatial continuity affect the performance of our models or not. The good thing about sequential Gaussian simulation is it's one of the most traditional approaches in geostatistics, so it has a lot of checks that could be used and adapted for the generative AI in order to see how good performant generative AI in learning the spatial continuity of sequential Gaussian simulation. So let's look into the checks. Check number 1 is a global univariate distribution, and for global univariate distribution, we check the distribution of the data. So we do have two checks, one for continuous data and for categorical data. So for the continuous data, what we do is that we take the distribution of the data and we flatten it. Once we flatten the distribution of the data for both training subsurface model and generated subsurface model, we estimate the overlap percentage between the two distribution, and we divide that by the distribution of the training images, giving us an overlap percentage of how good of a reproduction we have of the distribution of the data. The second check is we can check the percentiles, and we plot the percentiles of the training subsurface models and the generated subsurface models. And what we expect is, if we have a good model, to fall on the 45-degree line. But we're going to see some divergence. If we take that divergence and we integrate the area between the point and the 45-degree line, we're going to end up with a divergence area. What we are looking for is a model that have a very low divergence area, which allow us to have a better reproduction of the data distribution. Regarding the categorical data, we do use what's called a total variance distance, and that's basically the error in the probability distribution of the categories. So what we are looking for is a very low TVD, where you see as here a good reproduction of the proportions that are very close to each other. If you have a very far reproduction of proportion, you're going to have very high TVD compared to this one. So a consistent theme that we're going to see throughout this study is that we're going to have good reproduction and poor reproduction in order to have a baseline of what to expect when comparing the different models. Second, we check local uncertainty. And for local uncertainty, what we do, we generate 1,000 realizations, and then we calculate the standard deviation across all the pixels and the entropy across all the pixels, and then check how good of distribution we have. We do use the standard deviation for the continuous variables, and the entropy, here it's the Shannon entropy for the categorical variable. What we are looking for here is to have a good distribution of standard deviation, like we see on the left side of the two figures. What we do not want to see is poor reproduction like this, where you see clearly artifacts that exist here, or dead pixel like you see here. So if you see like a very low standard deviation or very low entropy, that means that there is not much variability in those realizations. Since these realizations are unconditional, if you see that you see very low entropy values, that means that the model cannot have variability at these locations. So if you pick an example, if this model is collapsing here to a facies of sand, and then you measure at the level of your well location, which is the same location as here as shale, your model is not going to be able to change the facies at that point or condition to that measurement at the level of the well location. Third, global uncertainty. And in global uncertainty, what we do is that we take our subsurface models, which are like thousands to millions of dimensions, and then we try to reduce the dimensionality of those subsurface models into two components. So this dimensionality reduction is going to allow us to compare the models compared to each other. So we're going to compare the training subsurface models in orange and the generated subsurface models in blue. What we are looking for is that the models should be mixed together and not concentrated in the middle. So what we are looking for is something like this, where we have a good reproduction and everything is well mixed together. If we see concentration in the center like this, that means that this model have a very low variability and the realizations are very different from the training subsurface models. However, this is still a visual check. So in order to ensure that we can adopt a practical approach and quantitative approach, we introduce what's called the overlap percentage. So the overlap percentage is calculated as follows. We're gonna estimate a kernel density estimator for the training subsurface models and another kernel density estimator for the generated subsurface models. And then for both kernels, we estimate the minimum at every grid. So we're gonna mesh this into, let's say, 100 by 100. And for every grid, we're gonna calculate the minimum KDE between the generated and the training subsurface models. And this is going to be divided by the KDE of the training subsurface models in order to get an overlap percentage compared to the training subsurface models, which is the reference. After that, we check the spatial continuity reproduction, and that's basically we can estimate the experimental variogram, and then we compare the experimental variogram to the expected value of the variogram, or what's called the average variogram. This could be compared visually like this, where you look at the different experimental variogram and you see they are different, but better here. Or we can use the delta variogram, which is the average error, and the spatial overlap. So what we are doing here is that we are estimating the error to this average variogram. And we are also estimating the fluctuation of the variogram, which is the result of the ergodic fluctuation. We see if the generative AI model is able to learn that as well. So what we are looking for is a low error and high overlap, and we want to stay away from the opposite, which is low overlap and high error. After that, we check for the local exactitude, and for the local exactitude, we estimate the mean square error or the root mean square error for continuous data, and the F1 score for the categorical variables. And the F1 score is calculated using precision and recall, which is elaborated in this figure. After that, we look into this check, and this check is for conditioning artifact. So if you look into these figures, you will see that there is some patterns that exist here. These patterns are in black with one dot in red. So the dot in red is a measurement at the level of the well location that we try to ensure that our generative AI model is matching that measurement. So for that measurement in red, we take 2 points to the right and 2 points to the left and 2 points to the north and 2 points to the south in order to see if we have a uniform distribution of patterns or there is specific patterns that shows up more than the other patterns. This have been developed by Dr. Perch during his PhD. And we are adopting it here in order to see if we do have artifacts of conditioning in our modeling approach or not. What we are looking for is a more of a uniform distribution like this. It's okay to have some fluctuations, but everything should be close to the 0.65 because overall we're going to end up with 16 patterns for 5 consecutive points. And we don't want to see some patterns dominating the distribution. After that, we go ahead and we check for the dynamic response. And for the dynamic response, what we're going to do, we build the water flooding simulation and we estimate the recovery factor from that. And then we can either visually look and see how good of recovery factor we are reproducing, or we can use metrics where we have epsilon p50, which is the error in the p50 recovery factor. And we also look into the overlap percentage between the uncertainty in the recovery factor. Check number 8, which is model stability. And for model stability, this have been basically developed by Di Federico and Durlowski from Stanford. What they propose here is that since we do have a mapping from the latent vector, which is the vector that we have talked previously, to building subsurface models, we expect that a small change in the latent vector should result in a small change in the subsurface model. And if we have this, we can use optimization algorithms because we are going to have a smooth transition between the different subsurface models, allowing for better optimization of the GenAI model by changing the latent vector in order to match the subsurface models that we need to match the data at. So we take that approach and then we bootstrap it. And what we do here is that we pick like 2000 ensembles or like n number of ensembles. And then what we do is that for every, well, we pick pairs. Yeah, like n number of pairs of latent vectors. And for every pair, we build intermediate increment between every two consecutive pairs, for example, 5%. And then we calculate the sequential, the structural similarity index, which is a similarity measure to see how good of continuity do we have. And then we summarize and we examine the distribution using these box plots. So an example is here where we have a latent vector that is getting input into the model. We can also have a label that is inputting into the vector, and then we pick a totally different latent vector and the label, and then we try to interpolate between the two using linear interpolation. What we expect is that we want to have something like this, where like this from 1 to 2 is only 5% change in the latent vector. It's going to result in the similarity of the models being very similar with a slight change between the two models. What we don't want to see is something like this, where the models collapse to one, like even a small change in like any change in the latent vector does not show a change in the structural similarity index, showing that we most probably have mode collapse and we only have one realization that is getting generated again and again and again. We also don't want to see this because this is like a discontinuity. And if you use optimization algorithm to optimize the latent vector, as such as we match the output, we cannot really match it because we have discontinuity in our latent. After that, we also use radon transform to check the object orientation. And for the object orientation, since we are going to be using channels in our model, we are going to use this radon transform to calculate the orientation of the channels. So what's going to happen here is that we are going to take, so this is like an example of an image with an object that is horizontally distributed, let's say. And then what we do is that we're going to place lines, and for every line, we're going to integrate the intensity of the pixels. So the intensity of the pixel is going to be how much white pixels compared to the total number of pixels do we have at that line. And then we're going to plot this here. So this is on the y-axis, we're going to have the number of lines. On the x-axis is going to be the orientations. And then we rotate until we build the sinograph. and then the sinograph in the middle where the energy is maximal is going to be the orientation of the image. And we do that for the different realizations. And then we have the object width. For the object width, what we're going to use is the Euclidean distance transform. And the Euclidean distance transform, how do we use that? Well, we are going to take an example like this. This is a model where you have a channel. For this channel, we're going to calculate the Euclidean distance of every white pixel to the background pixel, which are in black. And then we're going to have a distribution of width. And that distribution of width, we go ahead and we estimate a representative P50 or P25, depending on what calibration we use, and we use it as a representative value for the distribution of our widths. Now that we have introduced all the checks that we have, we're going to move and show what are the comparison that we're going to make between the different models. But before that, we need to introduce the training subsurface models that we are using. So we're going to have two types of training subsurface models. We're going to have unconditioned subsurface models and preconditioned subsurface models. So the unconditioned sequential Gaussian simulation are realization that are not conditioned to any measurement at the level of the well location. Think of them as random realizations. The preconditioned sequential Gaussian simulation are realizations that are already conditioned to measurement at the level of the well location. So let's say pick an example where we have like 5 wells, and in those 5 wells we have measurements, and we generate different realizations based on those 5 measurements. If we train our generative AI models, so the models that we have RVA, GANs, and DTPM on unconditioned realizations, is going to be called unconditioned model. If we train it on preconditioned sequential Gaussian simulation, it's going to be called preconditioned models. And this all happened during training. There is different type of conditioning, and it is conditioning post-training. What we do here is that we pick the variation, the unconditioned models that after their training, and we optimize the vector that we talked about, which is the latent vector, as such as we match the measurement at the level of the well location. So let's look into the models. VAEs or variational autoencoder. Variational autoencoder are a combination of two networks. We have an encoder and a decoder. So the encoder is going to reduce the dimensionality of the subsurface models into a low dimensional space. And the decoder is going to take the subsurface model, that small space, which is called the latent space that we talked about previously, and map it again to the same realization. And the cost function that we have here is that we are trying to reconstruct the same images that we are reducing the dimensionality of. So we're going to reduce the dimensionality here and then bring it back here. And we want to ensure that we are reconstructing the same images. But there is something else that we need to pay attention to, which is this latent vector. So this dimensionality is going to reduce the dimensionality into mean and standard deviation. And here we are assuming a Gaussian latent vector. From this mean and standard deviation, we're going to sample a Gaussian distribution, and that Gaussian distribution is gonna move move through the decoder to map into back to the subsurface models. The loss function also combine a KL divergence, and the KL divergence is what is ensuring that our mean and standard deviation are in a Gaussian distribution. Generative adversarial networks or GANs. This is also a combination of two networks. So we do have a generator and discriminator. The generator is going to take a latent vector, and this is the vector, like the Gaussian vector that we talk about. And then it's going to map it through the generator until we generate subsurface models. These subsurface models are labeled as generated subsurface models, and both these generated subsurface models and the real subsurface models are going to go into the discriminator, or the discriminator is going to learn to distinguish between the generated and the real subsurface models. The discriminator then sends feedback to the generator telling it that you are generating fake images, and the generator is going to try to improve the quality of the images as such as the generator can fool the discriminator. Both of these are trained in adversarial manner. So we're going to try to maximize the error of the discriminator, the error of the generator, and minimize the error of the discriminator until we train them in an adversarial manner, as such as the generator is trained, the discriminator is frozen, and then the discriminator is trained, the generator is frozen, until we get into an acceptable quality of realization. After that, we look into the diffusion model. And for the diffusion model, think about it as when you pick a droplet of ink and you drop it in water. So that droplet in ink with time is going to diffuse through the water. So we take the same example and we take subsurface models. And for those subsurface models, we're going to add noise in sequences. So let's say, for example, here we call them time steps and we add it in schedule until we end up with a Gaussian distribution of noise. And then for the reverse diffusion, we train a unit, and that unit responsibility is to learn how to denoise this image and bring it back to subsurface models. And it also happens in sequences. So the cost function here is that we are trying to learn what is the noise that exists within an image in order to denoise that noise from the image. So we take those we take all of the models that we have trained, and here you see we have unconditioned, preconditioned, unconditioned for VAEs and GANs, but we don't have that for DDPM, and I'm going to explain in a few. So we take all those models and we apply the checks that we have in order to compare the different models and see how good of realization or how if our models passes all the checks or not. So if we look into the diffusion models, here we are using denoising diffusion probabilistic models, and it's very hard to control the noise on this type of models. There is another variant that is called the DIM, which have better control over the noise, but we did not use that in the study. It could be an area of further research. Overall, we see that VAs are not recommended to be used for subsurface modeling decisions. They tend to under predict the recovery factor and fail most of the checks. GANs passes most of the checks, with some of the checks being tentative, i.e. they could be fixed using different variant. And the diffusion models perform very good. But since we could not condition or control the latent vector enough, we went ahead and we used GANs throughout the rest of the study. So I'm gonna pause here and then come back to continue in a few. Hello, back again. So after making the comparison of the models, we decided to continue with GANs in the rest of the study. And now we're going to move on to generative AI for history matching. And the problem that exists here is that the history matching current practice of generative AI that exists in the literature require retraining of the GenAI for every new case. Retraining the GenAI for every new case is going to be a limitation of adoption of generative AI. And the reason for this is because these models are very expensive. And if you retrain them, for example, our model here takes 3 weeks to be trained. So if we need to retrain every 3 weeks before we get any decisions, this approach may not be practically adopted for the industry. So what we are trying to do here is that we are trying to propose a new approach for the adoption of generative AI to be used for history matching, which is independent of the well location and allow us to perform history matching, which is going to increase the generalization of the approach and more practical adoption, especially by the industry. So the workflow is as follows. We're going to simulate subsurface training models. We're going to train the generative AI model, and then we're going to check those models. If they pass minimum acceptance criteria, we move to train an inference network. And I'm going to explain the inference network in a few. And then we check the conditioned subsurface generated models, and then we move to history matching. So the inference network here, what we are trying to do, we are going to try to divide the work. The generative AI model is going to be trained on unconditioned realization. So we're just going to be trained on generalized models. And then is going to be coupled with a lightweight inference network that connects to the generative AI model that is only responsible for conditioning. So here we divided the tasks. The generative AI model is going to be responsible of generating subsurface models, and the inference network is going to be responsible of ensuring that generated realizations are only matching the measurement at the level of the well location. So these are the realization that we generate, and the realizations we are generating here are 10,000 realization. We generate them using Petrel, and we assume parameters to be constant. For example, the width of the channel, the thickness of the channel, the orientation of the channel. These are parameters that we assume that are constant. And then we're going to train the generative AI model. So we're going to take latent vector, like for example, Z, map it through the generator in order to generate subsurface models. The discriminator is going to look into the training subsurface model and the generated subsurface models and send feedback to the generator. Note that in order to train the subsurface models, it took us 3 weeks. And another good thing that we notice here also is that this realization that we are generating here are 128 by 128 by 16. And if we calculate the total number of cells, we're going to end up with 262,000 cells. However, the generator that we use only have an input of 100 latent vector. So we were able to reduce the dimensionality of the problem from 262,000 to only 100 dimension, which is going to improve our capabilities of using automated history matching algorithms. After that, we check our generative AI models, and here we are using 5. We check for the global univariate distribution, local uncertainty, global uncertainty, local data exactitude, and model stability. So what we are doing here is that we train this generator that we are trained here. After we accept the training, we're going to couple it with an inference network. So the generator is going to be frozen, and the inference network is going to be trained here. So what we are going to do is that we're going to take a test case where we sample the measurement at the level of the well location, and then we're going to train the inference network as such as those generated subsurface models matches the measurement at the level of the well location. So the error is going to be MSE for continuous variable or binary cross entropy for categorical variables. So the inference network is going to take a latent a Gaussian vector here in W, and it results in a conditioned latent vector, which is Z star, where this Z star only points to directions in the latent vector that matches the measurement of the level of the well location. Another thing that we add here is we add a prior cost function, and the prior cost function ensures that all the conditioned vector here are Gaussian. And this is one of the assumptions of the GAN that we use, where we assume that the input is Gaussian. So we need to ensure that even the conditioned latent vector is also Gaussian. So we add a prior loss as well. Note that training these subsurface models or train the inference network only takes 6 minutes. However, training the generator took 3 weeks. So we went from retraining the generator on conditioned measurement at the level of the well location into just training the lightweight inference network for 6 minutes in order to update the generated realizations and match the measurement at the level of the well location, reducing the required time of building these subsurface models. After that, we take the combination of the inference network and the generator, and that is called condition generator. And we perform history matching. So what's going to happen here? We're going to start with a random guess of the input Gaussian vectors that goes into the inference network, and then that passes through all the condition generator. We generate subsurface models, and from that subsurface models, we run flow simulations. From the flow simulations, we're going to estimate the dynamic response. The dynamic response is compared with the measured response, and then we get an error. That error is used to update, used with ESMDA to update the latent vector or the input here. And we do that in iterations. Here we are using an ensemble of 200 elements in 25 iterations. Once we reach the maximum iteration, we're going to end up with an solution which are the 200 elements. So what is ESMDA? ESMDA is an ensemble-based approach that allows us to assimilate data. and yeah, assimilate data while accounting for uncertainty. So we're gonna have an ensemble of input, which is gonna result in an ensemble of output, and the way it updates the parameter is that the current parameters are dependent on the previous parameters plus the cross variance between the input and the output multiplied by the auto variance of the data by itself plus an inflation factor. And this inflation factor is adding some errors that I'm going to talk in a few. And all of this is multiplied by the error, which is the difference between the observed value and the simulated values. So the reason why we add this error is because we want the model to initially explore the different possible solutions and not limit it to a set of solutions. So think about it as initially the model is going to be more of explorative, and as we increase the number of iteration, the lambda is going to be dampening, and we're going to converge more into the solution. So it ensures that we cover most of the solution that exist. So now we're going to move into the checks, and here we are showing two checks: global univariate distribution and local uncertainty. So for global univariate distribution, we have total variance distance with a very small value and a very low error of less than 0.3%. So it's a good reproduction. And regarding the local uncertainty, we see here in the top is training subsurface models, and at the bottom is generated subsurface models. On the right, it's 3D estimation, and on the right, it's fence plot, fence diagram. And we see here that we have less than 1% error between these two, like the bottom and the top and the bottom for the local uncertainty. After that, we move to the global uncertainty. And as we have previously discussed, the global uncertainty is where we are trying to reduce the dimensionality of the subsurface models into a low dimensional space, and that low dimensional space, we compare the two models using the overlap percentage. We do see that we have very good overlap percentage between the two, the generated and the subsurface models. However, before we run this check, we had to choose which approach to use for the dimensionality reduction. And in order to choose which approach to use for the dimensionality reduction, we conducted an experiment. We generate 300 realizations of different orientations. We're going to have 100 realization of 0, 100 orientation of orientation 90, and 100 realization of orientation 45. And then we use three different dimensionality reduction approaches, including PCA, MDS, and UMAP, and try to compare which model is able to inherently learn that there is difference in the orientation of the models. And we see that PCA and MDS do not learn the orientation, but UMAP is able to learn the orientation. And the reason for this is because PCA work with variance and MDS work with distances of overall realizations. And in categorical data, this is very hard to estimate. However, UMAP work with building neighbor graphs and then try to reduce the dimensionality of that neighbor graph, which ensures that we are able to learn the orientation of the different realizations. After that, we check the model stability and local exactitude. So once we condition the realizations, we do see that for most of the conditioning that we have an F1 score more than 0.85, and this shows that we have a good conditioning. However, we cannot really ensure perfect conditioning, which is one of the limitations of our approach. If we look into the distribution of the latent vectors or the conditioned vectors, we do see that they are close to Gaussian distribution, which we think it's shows a very good sign of a good training and the good learning of the and the good showing a good showing that the model preserved the Gaussian distribution of like the inference network after it's trained, it's preserved the Gaussian distribution. Looking into the stable the model, we run 2,000 pairs, and then we can estimate SSIM for every 5% increment between 1 and 2. And this is for consecutive changes in the latent vector. We do see that we have very good stability of the model, showing that most of SSIM values are higher than 0.7 or about 0.8 on P50. So we can use this model for historic match. Now, for the history matching application, we're gonna generate two synthetic cases. These synthetic cases are generated using test case that was never seen by the generator. So we generate this using Petrel, and then we go ahead and we extract the measurement of the level of the well location, and we use it. Uh, so yeah, and we use it to train our inference network and then do the history matching. But the case here, which is the truth, what we are gonna do here is that we're gonna do two cases. Case number one is gonna be three wells, one injector, two producers, and this is gonna be running for 15 years. At year 15, case number two is going to introduce an additional three wells, which is going to be injector two, producer three and four, and we're going to run for an additional 15 years and see if our case can update to new measurement at the level of the well location, where traditional approach cannot really update that. The assumptions here is that for the sand, we assume that the permeability is 150 millidarcy, and for the mud, it's going to be zero point 0.1 millidarcy. The porosity is constant throughout all the model, and our injector is injecting at 20,000 barrels per day, where all of our producers are producing at 10,000 barrels per day. So what we do here is that we take our pre-trained GAN that learned how to generate unconditioned realization, and we train the inference network. So for case number one, you're going to see the realizations here, and here we are checking for the local uncertainty. We do see that our models still have a lot of variability outside of the well locations, and the F1 score is at 0.93. After that, for case number two, where we have six wells, the uncertainty drop a little bit, but we do still have uncertainty in the model, and we have an F1 score of 0.95. So we have good conditioning and still have good variability of the model for uncertainty. After that, we go ahead and we run our history matching algorithms. So what you're going to see here, and this is consistent, you're going to see the prior on the left, the posterior on the right. The gray is the uncertainty. It's like between P5 and P95. The red is the observed data, and the blue is the mean of our realizations. Since we are using ESMDA, we're going to have 200 ensemble, and this is the mean of 200 ensemble. We do see that from the prior to the posterior, we do see a very good convergence toward the solution, a reduction in uncertainty, and a very good history matching results. However, if we take case number one, and we take the posterior where we have history matching data, and simulate that we add additional three wells for case number two without doing any history matching, we see that our model have very high uncertainty and basically does not capture any measurement. And this is like simulation of using the traditional approach. This is an approximation of using the traditional approach where we train our model on preconditioned realization. If we have an update in the data, we need to retrain the model. Here we see that without retraining the model basically fail, and we cannot really match the dynamic response. However, if we retrain our inference network and we look into the results, we see here, this is the same results for the first three wells, but this is for 30 years. The first one was for 15 years. And the dashed line is where we implement the new wells. We do see that the uncertainty drops, and we do have very good history matching. And the same thing for the additional three wells that were drilled at year 16. We do see a good history match. Something we notice that is interesting is that even the prior of our approach is better than the posterior of the traditional approach. So you see here the prior, which are these results, overall have better convergence compared to not updating the data. So we see that our approach results in better history matching and reduces the error up to 3.6 and 8.3 and 3.6 psi for the additional wells that are here. So as the key takeaway from this study is that we have proposed a coupled model approach where we combine pre-trained generative AI. It could be GAN or it could be an adoption of another model with an inference network for conditioning. So we have divided the work where the generative AI is going to learn how to generate models, and the inference network is going to learn how to condition them. we were able to achieve 1 to 5,000 speed up of retraining of generative AI models. And we see that the minimum acceptance checks have been passed by our models. And we believe that the introduction of this workflow is going to increase the practical adoption of generative AI for history matching, unlocking more efficiencies in the practical adoption of this approach. All right, now let's move into the last chapter, which is generative AI for uncertainty quantification. And the challenge here is that looking into the historic performance of the exploration project of the oil and gas, we noticed that most of the project underperformed 15% compared to their expected value. And the reason for this, and this could result in suboptimal decisions or some even project to fail, where the decision was made to invest. So one of the reasons here is that there is an oversimplification of the quantification of uncertainty, especially scenario-based uncertainty, because of the iterative nature of this workflow that requires a lot of human efforts and professional time in order to assess the uncertainty, which may not be feasible in the time frame of the project. So the solution that we are trying to propose here is a streamlined approach that allow us to integrate the scenario-based uncertainty even as a knob. So, for example, the geoscientist can test different scenarios and see which parameters satisfy the measurement at the level of the well location. This model could also be deployed for history matching in order to match the dynamic responses. So up to now, we have been talking mainly about generative adversarial network or GAN, where we have an input latent vector. The generator generates subsurface models. The discriminator look into the subsurface models and compare them with the real ones, and then we update the generator and update the discriminator in a competitive manner. One thing that we add in order to include the scenario based is that we move into conditioned GAN. And the conditioned GANs take a label in addition to the latent vector. Think about label as the prompt that you send to ChatGPT. And here, the discriminator and the generator are going to be generating or classifying images based on their label. So let's take an example. For example, if we ask from the generator to generate a channel deposition environment with 4 channels, the generator, let's say, for example, is going to generate channels with a channel model with 3 channels. Even if the quality could be very high, the discriminator is going to say, no, I wouldn't accept this because the labels that you have provided here are wrong. So the discriminator is going to only update given a label. So the probability distribution is going to change from matching the data into matching the data given a label. So the workflow becomes as follow in order to demonstrate the case or the in order to demonstrate our workflow. We're going to start by generating labeled synthetic data. We're going to train a conditional GAN, check the realization, and condition to hard data using data assimilation approach. So regarding the labeled synthetic data, we generate them using Petrel. We generate 80,000 realizations. Each realization is going to have a different orientation, different proportion, and a different width. So we're going to have different values of width, different values of scent proportion, and different values of scent orientation. After that, we train our conditional GAN, and then we check the realizations. Here we are using 6 checks. We use global univariate distribution, object orientation, object width, local uncertainty, model stability, and local data exactitude. And then we go ahead and we condition to hard data. So now the training becomes as follows. We're going to have a generator. The generator is going to take a latent vector, which is Z, and a label, which is the properties that we have here, the orientation, the proportion, and the width. And at the same time, the discriminator is going to look into training subsurface model with their label. And the training is going to be done given a label. Note that in order to ensure that our model is able to learn the orientation, specifically the orientation of the channel changing, we try a parameterization trick where we do not really input the orientation directly, but we estimate the cosine and the sine of the orientation, and then we input it as a label. This will allow the generator and the discriminator to learn the circular nature of the orientations instead of thinking that as you increase keep increasing the orientation, something else may happen. And then moving to the data assimilation is going to be a little bit of a similar workflow. We're going to start with the random uh, latent vector along with labels, randomly selected labels. Here we use the uniform distribution for the labels and a Gaussian distribution for the latent. These are going to be mapped through the CGAN, generate subsurface models. From those subsurface models, we're going to extract measurement at the facies location, which are similar to the same location that we have measurement in the field. And then we're going to estimate the error and then update, use ESMDA to update both the label and the latent vector. So here we are updating both the label and the latent vector. Note that this workflow could be adopted for geophysical data, dynamic responses, by changing this transfer function that we use here. For this exercise, since sampling well at the level of the well location is cheap, we use a large number of ensembles, which allow us to explore more potential solutions that exist. So looking into the model ability to learn the realizations, we do see that the model was able to visually, like by looking them visually, we see that the model is able to learn how to increase sand proportion, how to increase width, and how to increase orientation by looking to these pictures. There are very interesting observations that we can also look at. For example, this channel is looking toward the left, and it's cutting here toward the end of the edge of the image. And once we add only 5%, this channels become a full channel within the image. This shows that the model can really learn that it can learn to not add channel directly, but add in a gradual manner. So it's gonna try to add into the edge and then move toward the center. And we see this also here, where we went from 35 to 40. The model started adding from the edge, and then this started moving toward the left, and then adding more and more channels. If we look into the width, the model started with about 3 channels, and then we see as we increase the width, those channels merged. And then we see that the channel toward the left started moving toward the edge in order to reduce, in order to keep the proportion constant. Regarding the orientation, we do see that overall the model is able to learn different orientations and generate different orientations for the image. However, we think that this visual inspection is basically subjective and we need a more objective quantification of these parameters. So we go ahead and we run our random transform for the orientation, Euclidean distance for the channel width, and we count the facies proportion and we compare them. Note that every box plot here is 500 realization, which ensures that we have a robust check. And the colors here in purple are subsurface training models, and in orange are generated subsurface models. In white, these are interpolation. So these are labels that were never seen by the GenAI, and the model was able to learn the interpolation between the two. We do see that overall our model was able to learn the distributions, including facies proportion, channel width, and channel orientation, showing that the model successfully learned these scenario-based or model parameters. We also check the local uncertainty, and we do see that the uncertainty of the entropy and the orientation are well reproduced, and in addition to the proportion. Something interesting we see here in the proportion is that the uncertainty in the proportion increases until 50% and then decreases. And the reason for this is because toward the two ends of the sand proportion, if we are at 70%, we have mainly sand, which reduces the local uncertainty. And if we are at 30%, we are mainly mud, which also reduces the uncertainty. Next, we check model stability and local exactitude. Here in blue, we see the similarity between two consecutive latent and labels. So what we are doing here is that we are picking two random, like a pair of random label and the random latent vectors, and then we interpolate between them. We do that 2000 times, and the interpolation between, so this is going to be vector number one, this is going to be vector number two, and all in the middle are linear interpolation between the two vectors. And the increment is 5% for both the label and the latent. In blue, we do see the comparison between two consecutive labels, and in orange, we see comparison with the initial image. So the comparison with the initial image shows that we are deviating very far from the initial image, showing that we don't have the same image. And the consecutive similarity shows that we have a continuous latent vector where a small change in both the label and the latent results in a small change in the realization. Looking into the conditioning check, we achieve a perfect conditioning for all the the different number of wells. And note that for every case here, we repeat this 300 times. And like for every number of wells, like for every time we try to repeat this, we pick a random location of wells, showing that the model is robust for different wells location and different number of wells. After that, we are going to show two examples, and the examples that we are showing here are for conditioning to the measurement at the level of the well location. So we're going to have two data assimilation cases, case number one and case number two. This is case number one, and as you see, this is the case number one here. Case number one have an orientation of 0, a percent proportion of 60, and the width of 250. Note that these labels were used during training, but this realization was never seen by the model. We have two cases, a case of 9 wells, a case of 25 wells. The case of 9 wells here initially, we are going to start with uniform distributed labels and random selected Gaussian noise. The proportion is in purple. In green, we have the width of the channels, and in orange, we have the orientation. The dashed lines are the true values. So we start with initial guess, and then we converge, and we see that the model converged toward the correct solution, reducing the uncertainty, but we do still have a very wide uncertainty range. And this is usually overlooked by the practitioners who uses these approaches who assume that they already know the parameters. For 9 wells, there is plenty of parameters that we can use that can match our distributions that you can see here. As we increase the number of wells, we see a reduction in uncertainty, but we do still have a very wide range of uncertainty that all honor the measurement at the level of the well location that we see here in red circles. If we go ahead, and what we do is that after our model converges toward the end of the number of iterations, we estimate the mean or the average of the pixels to see if on average we were able to reproduce the same realization. And we also estimate the entropy across pixels to see how much uncertainty do we have. We see that for the ensemble mean at 9 wells, we basically almost know nothing. And this shows that our realizations at 9 wells, we have a very high uncertainty that we cannot really assume any model parameters to match the measurement at the level of the well location. The uncertainty only drops at the level of the wells. As we increase the number of wells to 25, we see that we were able to more of reproduce the same model because we increase the number of wells. However, there is still some subtle changes. For example, this channel that exists here is replaced by two channels that are in the middle. And also there is still high uncertainty in the edges of the channels and where they exist. This could be solved by including the dynamic response, because as the pressure field the boundaries, we can have more information. Example number 2. And this is using an orientation of 40, proportion of 55, and the width of 170. Note that the model didn't see any of those labels during training. And we perform the same case, 9 wells here, 25 wells here. We do see that we have a reduction in uncertainty at 9 wells, and that reduction in uncertainty drops even more at 25 wells, but we do still have very wide uncertainty range. Looking into the average, we do see here, for example, for 9 wells, the model only captured half of the channels that exist here and didn't see both of those channels because there is no well that exists there. And this could result in in reserves that are not explored that may exist there because we did not account for that uncertainty. As we increase the number of wells, we are able to reproduce more of the realizations that we have, but we do still also have uncertainty in the edges of the channels or the width of the channels. So key takeaway is that we have extended the application of generative AI to include different geological model parameter, providing a way to capture scenario-based uncertainty. The scenario-based uncertainty here shows that there are different model parameters that can match the measurement at the level of the well location. And if we don't include this, we can result in suboptimal decisions. The CGAN is checked against minimum acceptance checks, showing that we passes most of the checks, showing robust performance and trust in the model. So as a final summary, we extend the minimum acceptance criteria protocol for the generative AI-based subsurface modeling, and we provide a robust framework for checking generative AI subsurface models. We have developed a comprehensive comparison framework where the models have been compared against different tasks for geostatistics. And we developed a new generative AI-based history matching approach that's independent of the well location in order to ensure more practical, efficient adoption of this approach. And we were able to extend the abilities of generative AI-based workflow to quantify scenario-based uncertainty in order to ensure better informed decisions. So these are the publication that I have done during my PhD, and I have only presented the first 4 that are here. And I would like to thank my supervisor, Michael Perch, my committee members, my family, friends, colleagues, and mentors. And as part of UT, I was able to stand on the shoulder of giants who taught me a lot of things. Thank you very much for following this, and let me know if you have any questions. You can drop them in the comment and I will try to answer them.